Well, thank you for joining me on this question. This question says to sketch the function f of x is equal to 2x minus 3 squared plus 4 using the domain 0 to 6. X is between 0 and 6. So let's have a look at a y-axis and an x-axis. And we're going to use the domain from 0 to 6. So we don't need the negatives. Well, let's have a look at this function here, and it's in the form where you can take y equals x squared as a quadratic, which is like the parent function. Parent function is a quadratic, normal quadratic x squared. So it goes 0, 1, 1, 2, 4, the usual 2 squared is 4, the usual quadratic, negative 1, 1, negative 2, 4. But our quadratic has a x minus 3 squared. Now minus 3 in with the x means it's been translated, translated 3 units to the right. Notice it's minus, and if it's a translation to the right, we've got an x minus some constant value, which is how many units it slid to the right. If it slid to the left, it would be x plus 3. So we take our function and we slide it 3 units to the right. So instead of at 1, 1, it's at 4, 1. Instead of at negative 1, 1, 1, 2, 3, it's at 2, negative 1. Instead of negative 2, 4, it's at 1, 4. Instead of being at 2, 4, it's at 5, 4. And here is the function 3 units to the right. Well, let's have a look at this double. A double is when we've got a 2x minus 3 squared. That's like a stretch of a factor 2 from the x-axis vertically, because it's doubled all our y values. So instead of going up to 1, it's doubling, it's going up to 2. Instead of going up to 4, it's doubling, and it's going up to 8. Instead of going up to, well, double 0, 0, and instead of going up to 1, it doubles up to 2. Now, if there was a negative value, it would stretch it down, but we don't have that situation. So we've got our new graph. I'll do this in blue. Is our graph has been stretched two times from the x-axis. Now we've got this plus 4. Plus 4 means it's a vertical movement. We simply add 4 to the y value. So everything is its translation, translates 4 units vertically. Well, let's do this in, let's go back to red, because I don't have a red one yet. Up 4, 1, 2, 3, 4. The position 2, 1 goes up 4, up to 2, 6, 2, 3, 4, 5, 6. And 1, 8 goes up to 12. 1, 12. So we're going to get this situation. Instead of 4, 2, goes up to 6. Right, so let's draw that. Where's our x-axis? Okay, so we want from 0. If you substitute 0, you can find out the starting point. 0 minus 3 squared plus 4 equals 2 times 9, 18, 22. So it's going to be 22. So let's go 10, 20, 30, 5, 15, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 10, 3, 4, 2, 3, 4, 20, 3, 4, 25. Okay. So we want at 22. 0, 22 is the starting point. 0, 22 in the domain. When it finishes, it's going to be, we need that space, so I'll just do it over here. Function of 0 is 22. The function of 6, where is it leaving our zone? 2 times 6 minus 3 squared plus 4. So it's 2 times 3, 9, 18. Oh, it's 22 again. So 622. Its final point. We don't go out of our domain. We stay between 0 and 6. Now let's go in these points here, and we see that it's turning at 3. And if you substitute 3 in there, you can get 2 times 3 minus 3 squared plus 4 equals 2 times 0 plus 4 is 4. 3, 4. That's our minimum point. And the other points we've already determined are 2, 6. 4, 6, 1, 12, 5, 12, and here is our parabola. And don't put arrows, do not put arrows, because it's starting and finishing at those points. So I hope this has helped. But before I close off, looking at this graph, I want you to be able to see that it's the original parent graph, moved 3 units to the right, so it's turning when x is 3. You can find the y value by substituting. It's stretching it at double, and it's raising everything by 4 units. So the turning point here, you can see, will be 3, 4. Just by looking at the graph, the turning points will always be 3, the x value, 4, up 4. Until next time, stay happy.